Hello, good morning everyone. Today, inshallah, we will go through chapter, I believe, 6, which is the eigenvalues and eigenvectors. This chapter is really, very important. And it is really simple. I will start this lecture by going through the method quickly, which is how to find eigenvalues and eigenvectors in details. It's really very simple. All you have to do is to solve a homogeneous system of equations, as you will see. I will be able to find the dimension of the eigenvector space, and so on. We can continue for the diagonalization and for the rest of the problem. Today, it has a lot of details. You will have to focus with me as much as possible, and please try to solve these equations using your hand. Of course, within the next lecture, inshallah, I will finalize this chapter and I will go for the next chapter, which is about the inner product and so on, as you will see. Once more, as I told you, we are here in eigenvalues and eigenvectors. Hopefully, this chapter, inshallah, I will try to finish it within the beginning of next week. At the worst case scenario, it will be finished on next Monday, inshallah. Then I will go for the linear geometry. The other two chapters are very, very simple. And once more, as I told you, the eigenvalue and eigenvector chapter is very simple. All you have to do is to try to solve these problems once more using your hand. It's a skill for finding the eigenvalue and eigenvectors, and the steps are really, very simple, as you will see. Okay, let's start. Eigenvalues and eigenvectors, story to be told. Okay. Let's go skip those slides just in a second. So the reason for the use of eigenvalues and eigenvectors, it is the simplicity of dealing with matrices if it is on the diagonal form. So for example, if I have this matrix, which as you can see is a diagonal matrix. If it is to the power of 10, it's really very simple to evaluate the value of this matrix. Because simply, it will be negative 1 to the power of 10, 3 to the power of 10, 2 to the power of 10. According to the multiplication process. Of course, it's really very simple to deal with this case with a power or whatever than dealing with this matrix. Also, especially if these two matrices are similar to each other, and we will know within the next slides, actually, what's the similarity or what's meant by the similarity between two matrices. So dealing with this guy is much easier than dealing with that guy. The eigenvalues and eigenvectors have plenty of applications, not just only in linear algebra, but in all the other branches in mathematics, and also within huge applications in STEM in general, science, technology, engineering, and mathematics. Of course, there is a way to simplify the communication on the second case. This is the case that I'm telling you about. Two matrices A and B are similar if there is a matrix P, and we will be able to find this matrix, which is the P matrix. This matrix will make A, which is in the general form, into a diagonal matrix called the B. And it is similar to this one. This is why we are having this technique for P. If A is similar to a diagonal matrix, then we can take advantage of its properties. That's the bottom line of what we are doing. Okay? Okay, once more. So our mission now is to find the P matrix, which is going to be, if it exists, it's going to help us to get a similar matrix to A with a diagonal form, so it will make your life easy. Okay, my way. We will get back to many slides shortly. In this lecture, I will divide it in two parts. The first part, I will go with you on how to find the eigenvalues and the eigenvectors for a matrix. I will use the simplest ones with a 2 by 2. Same rules will be applied for 3 by 3, as you will see. But it's a very successful tool to translate or to deliver the idea of how to evaluate all of them. Okay? The eigenvalues and the corresponding eigenvectors. So I will start with this, with these matrices. First of all, what's the U matrix, which is the eigenvector, and what's the eta, which is the eigenvalues. Once more, if I have A times U, A is a general matrix, preferably if it is a symmetric matrix, as we will see down the road from the quadratic forms, and u in the vector that we are dealing with, we will find that a times u is equal to certain scalar value eta times u. So, for example, if I have a 3 by 3 matrix, u is going to be a vector 3 by 1. And if you multiply these two guys together, the result will be eta times the eigenvector. So, once more, eta the eigenvalue and u the eigenvector. That's the principle that we want to find. We need to find eta, then we need to find u, which is the vector. If you multiply them together, it's going to be exactly the same, like multiplying the eta times u. Are you with me? Okay, how to solve this equation? It's very, very simple, Ziad. All I have to do is to move this guy to the other side. So if you move eta u to the right-hand side, to the other side, you will have, to the left side, you will have au minus eta. So if you take u according to the matrices properties, okay, as a common, from the right-hand side, you will end up having a minus eta I times u equal to 0. So if you have an equation of two parts multiplied in each other and it's equal to 0, it's really very clear. Either one of these two guys is equal to 0. If u is equal to 0, which is a vector, so it's a trivial solution. So anything you will multiply it in a vector of zeros, the result will be an origin. Am I right? So the only solution to this case to make sense is to have a minus eta I is equal to 0. And this is the system that we will depend on in order to find both the eigenvalues and the eigenvector and the corresponding eigenvalues. So where u belongs to Rn, it's a vector relative to Rn, to the dimension of the matrix, except 0. So u cannot equal to zeros. Am I right? Because it's going to be a trivial solution. It's a logic. And eta belongs to R, which means it's a scalar. By the way, it's supposed to be eta belongs to K for generalization. So it can be a real number or a complex number. And we will go through this down the road. So eta is called the eigenvalues. And for each one of these eigenvalues, I will have an eigenvector corresponding to it. That's the story of eigenvalues and eigenvectors. Okay? Very, very simple. So once more, I have a minus eta I u equal to 0, given u doesn't equal to 0, so the only solution is a minus eta I is equal to 0. That's the way that we are going to use. So the only solution, if the a minus eta I equal to 0, then the determinant of this matrix, is also equal to 0. And this is what's called the characteristic equation, that I will depend on finding eta values. So once more, the story starts like this. I have an A matrix times a vector is equal to some constant times the vector. Already I've succeeded in bringing them all to the left-hand side, so I ended up with this matrix equal to 0, which is a function, okay, in the A minus eta I, which is going to develop the eigenspace. Okay, at the same time, once this matrix is equal to 0, so its determinant will be equal to 0. A minus eta I is equal to 0. Once you expand this equation, it's going to be a characteristic equation, as you can see, from which I can find the eta values. After finding the eigenvalues, I will use this system in order to find the eigenspace. Back again to this to the general case of A minus eta I times u equal to 0. Let's go through these steps. It may look to you a little bit strange, but once you apply it, you will find it's really very simple and very smooth to evaluate. So let's start with this problem. Look to this problem. I have a matrix. I've chosen simple and symmetric matrix, as you can see. And also dealing with the quadratic equation, with the quadratic forms down the road. In the best cases, we will have a symmetric matrix by this one. So if I have 9, 2, 2, 6, which is a matrix, I need to find the following. First of all, I need to find the eta values, which are eigenvalues. Then after finding these eigenvalues, sometimes we call them spectrum. After finding the eigenvalues, I will use these eigenvalues to find the corresponding eigenvectors. From most of them, I will be able to get the matrix P, okay, or the also normalized model matrix. Here I'm taking the symbol U because this is an older slide with respect to our slides, okay? Okay, a check and the definition, very important one. In a very beautiful type of matrices, which are the orthogonal matrices. Ziad, what's an orthogonal matrix? It is the matrix which its columns are perpendicular in each other. What is the relation that will show you if you have two vectors that they are perpendicular to each other? If you multiply them together with a dot product, the result will be equal to 0. We will come to this point. But for the orthogonalized or for the orthogonal matrices, it has a remarkable property, which is its transpose is its inverse. So once more, one of the great advantages of using the eigenvectors for a symmetric matrix, you will develop an orthogonal matrix. The orthogonal matrix has a wonderful probability. What's the probability of the orthogonal matrices? Its transpose is its inverse, which is amazing. So after you find this matrix, this check will lead to U transpose times U is equal to R. Please concentrate on it. And if you get U transpose times A times U, you will end up having a diagonal matrix, and that was our goal from the beginning. So, very happy that you came here. Okay? Now, I will start the procedures, step by step. The previous part, you can watch it, okay? But now it's very, very important to find the eigenvalues or the eigenvectors. It's a systematic way, but I need your full concentration. Okay? So, the first step, as we said previously, all I have to do is to use the characteristic equation. What was the characteristic equation, if you remember? I have the determinant of the A matrix minus eta times I. This determinant is equal to 0. You know the story. We already told the story previously. So I will deal with this case. Look at this case. This is the A matrix. Of course, for this to be correct, the I matrix should be a unit matrix, but of the dimension 2 by 2. And the eta, as I told you, is just a star. So let's do it together. Substituting in this equation in that form, you will find, okay, it's gonna be a determinant for the matrix, which is 9, 2, 2, and 6, then minus eta times the unit matrix of the same dimension, which is 1, 0, 0, 9. That's the determinant, and it's equal to 0. Yes, you are correct. This is gonna, once you evaluate this value or this determinant, it's gonna be an equation. Let's do it together. So once you finish up these two matrices, you will end up having the following. You will have this determinant or the determinant of this matrix. Log to the matrix. It's very, very simple. And it's a key unit. It's a 9 minus eta. And this is the number 2, and that's 2, and you will have 6 minus eta. Because once you try to substitute, you know in the addition and in the subtraction of two matrices, you add or subtract the corresponding elements. So it's very smooth, okay? You will end up having from the first block, okay? You don't have to write all of those. But I'm writing this in order to make the steps look logical, but it's very easy to evaluate. So if I want to evaluate the eigenvalues, all I have to do is to take the principal diagonal minus eta, and then evaluate the value of this determinant, as you would see. Let's evaluate it together. Come on, man. Multiplying the elements of the principal diagonal will lead to 9 minus eta, am I right? Times 6 minus eta minus 4 is equal to 0. I need a solution for this equation. I need a solution for this equation. So it's gonna be eta squared, am I right? Then you will have negative 6, negative 9, so it's coming up to negative 15 of eta. Then you will have 6 times 9, which is 54, am I right? Minus 4, so it's gonna come up to plus of a 50 equal to 0. Are we all aware of it? Is it correct? Yeah, but it is correct. You have to have this step correct. Okay, now I can analyze it and I can solve this quadratic equation in order to get the values of eta, which is really a piece of cake. So it can be analyzed as the multiplication of two vectors equal to 0, eta, I believe 10 and 5, this is minus, that's minus. Am I right? So now I have the eigenvectors. So the solution set of this equation is what's called eigenvalues. So it's going to be eta 1 is equal to 5 and the eta 2 is equal to 10. Now I have these two values of eigenvalues. Remark. If this matrix was a 3 by 3 matrix, how it's going to be done?
No way.
It's exactly the same. But you will have a cubic equation instead of having a quadratic equation. I will go with you through a necessary steps of how to solve a cubic equation according to the theory of equations later. But to keep our discussion smoothly with you, I will keep it for 2 by 2 for the time being. Okay? So now I have the eigenvalues. I can solve the system. Mr. Ziad, do you remember the system that we were dealing with mainly? The system was like this. It was the matrix of A, okay, am I right? Minus eta of a matrix I, both of them multiplied in U, and all of them is equal to 0. Now I found the values of these guys. What's required? No. Leave this form completely. Now I need to find those guys. This was the matrix at the beginning. Do you remember? I have A times U equal eta times 0. So this is the system that I was dealing with. Yes, Ms. Nada, if you look to this system, you will find it's a homogeneous system of equations. Simply because this is a matrix 2 by 2. Am I right? And this guy is known at the time being. Am I right? And that's the only unknown here, which is U, which is a vector. This is going to be a matrix 2 by 2. So this guy is a vector, which is going to be dimension 2 by 1, and it's equal to 0. Now I will have to solve for the solution of this vector. And already you know from the beginning that U is never equal to 0. Because if it is equal to 0, you will be dealing with a trivial solution for a vector with components 0 and 0, and you will end up having 1. Am I right? So let's do it. I will start with evaluating the vectors U1 and U2. What's the vector of U1? Eigenvector. Relative to the eigenvalue. Are you with me here? Let's do it. I will start like this. Okay, once more, I will do the following steps. Now, I am getting U1, which is the first vector, which is of course relative to eta 1, which is equal to 5. And in a similar manner, I will do the same steps in order to get the vector U2, which is automatically which will be corresponding to eta 2, which is equal to 10. Yes, Zia, your question is correct. What if I solved this quadratic equation and I just replace these two numbers? So this is eta 1 is equal to 10 and this is eta 2 equal to 5. It will make no difference. I will get the corresponding vectors relative to the arrangement of my calculations of the lambda vectors. I'm sorry, to the eigenvector. to the eigenvalues. Are you with me? Okay. Now, don't try it, don't do anything, just focus on it. I will do substitution here. So I'm substituting instead of beta by the value of 5. So all I have to do is to get back to this matrix, making the substitution to happen, which is 9 minus a 5, am I right? 2, 2, 6 minus 5, which is a system of a homogeneous system of equations according to this equation. That's the augmented matrix. Am I right? This augmented matrix will find the values of the components or the coordinates of the vector U. Okay? So, this guy, as I told you, is a vector. U is a vector which contains U sub 1, first component, U sub 2, second component. X, Y, A, B, whatever. But I would like to write them, me, myself. I would prefer to write the first vector, first component, the second, the first vector, second component, the way that I'm writing it. Okay? Okay? Let's solve it. The first step, 9 minus 5 is going to be 4. And this guy is 2, and this is 0, then you will have 0. 1. 6 minus 5 is equal to 1. And look closely to this system. It's an infinite number of solutions. Once you do the solution, the substitution of the eigenvalues, you will end up having infinite number of solutions. Actually, you are forcing this system to be on this floor. In another words, okay, once you do the substitution, you should remark a relation between your rules. In 2 by 2, it's going to be very obvious for you. There is a relation between these two rows, am I right? So just only multiplying the first row in negative half and then adding it on the second row, you will have zeros. It must happen. It will have to happen because you are forcing it. Are you with me? So this system, this method, simply can be put on this form, Mr. Ziad. 0, 0, 0. I need to get the reduced echelon form. So I will not divide the first row on 4, yes, yeah. Right. So it's going to be a 1, then 0.5 and 0. Am I right? Dividing on 4, the first row. Correct. Now I have the reduced echelon form. Now I can find the infinite number of solutions. Let's expand them once more into an equation. So it's going to be the first vector, first component. The first vector, second component. Am I right? Expand as an equation now. 1 times U sub 1, so it's going to be 1, 1. Then 0.5 times U1, 2, so it's going to be a plus of 0.5 U1 second component. And the most of them is equal to 0. So now you have an advantage of knowing that the first component is equal to negative half of the second component. Am I right? Now I can get the vector. The vector U1, the first vector, actually consists of how many components? 2 of them. So that's the first one, U sub 1. That's the second one, U sub 2. Now I will use this relation by substituting instead of U sub 1 by negative half U sub 2. So it's going to be minus 0.5 U12 U12. Of course, you are right, it's an infinite number of solutions. So the 2 components depends on the value of U12. And according to the vector spaces that we led a fight in evaluating them, now I can have the basis of the eigenspace of the first eigenvector, which is really very simple. Take U12 as a common. So you will have minus 0.5 times, U12 as a common, you will have negative 0.5 and 1. Am I right? Yeah. This is an infinite number of solutions. So any value of U12 you consider is going to be correct. Am I right? Okay, let's be smart at this point. I will need any values except 0 for u1, 2. What's it gonna be yet? To have integers, to avoid fractions. I would choose u1, 2 is equal to 2. Simply because 2 times half is gonna equal to 1. So now I have the basis of the first eigenvector. This is u1, the first vector, which is gonna be with the basis, which is simply -1 and 2. Am I right? So all the vectors on the shade, -1 and 2, it's gonna be an eigenvector corresponding to the eigenvalue which is equal to 5. Is it simple?
Easy.
Let's do it once more. But this time it's gonna be with 10. Do it. So simply it's gonna be
-1.
yes, 9, but let me write it for this time. 9 minus 10 to 2, and then you will have 6 minus 10. Are we right? And this system is going to be the augmented matrix. You don't have to write the zeros, but I usually feel more comfortable doing it like this. And of course, that's a system of equations, as you know. So I will simplify it and make your life easier. So it's going to be a -1, 2, then 2, then -4 is equal to 0. Do you still have the link between the vector, between the two rows?
Yes.
Yes. They are multiples of each other, am I right? So simply, if I multiply the first row in 2 and then add the result to the second row, it will disappear. Okay? And then I will get to reduce the echelon form. Yarada, is it clear? ثانية, if you multiply this by 2, -2 plus 2, 2 by 2, 4, -4 is going to equal to. It's a must have. So multiplying the first row in a negative, you will have 1 minus 2 and equal to. Now I'm evaluating u2, which contains how many components?
2.
So it's going to be the second vector, first component, second vector, second component. Are we right? Excellent. The dimensional equation, please. So you will have u21 is equal to 2u2 sub 2. Am I right? Once more, the second vector u2 consists of how many components? u21 and u22. Am I right? Use this relation to substitute. You will have 2 and 1. Am I right? Times u2 sub 2. And in a similar manner, you will have u2 basis as
2.
2. صح؟ حلو مش كده؟ Okay, a remark. If this matrix is a symmetric matrix, you will have orthogonal vectors. Look to those vectors, they are orthogonal. How to know if they are orthogonal? This vector and that vector, how is it going to be orthogonal? If you get the dot product, the inner product, we'll go through these relations within the next chapter. So if I multiply -1 times 2, it's going to be -2, plus 2 times 1, which is 2. The sum of them is equal to, yes, u1, you are right, u1 dot u2 is equal to 0. In this solution, now I found what's called eigenvectors. They have to be. If the matrix was symmetric, yes. If the matrix was not symmetric, it's not. Okay? But we are talking about an ideal case here, Mr. Ziad. So it's coming to this. Remark, more than one point measuring. Mainly, I want to tell you about them. For the time being, I want to define what's called an algebraic multiplicity. Once more, algebraic multiplicity, which is the repetition of the eigenvalues. Once you solve this problem, the eigenvalues was distinct. Am I right? 5 and 10. Okay? So the algebraic multiplicity for this root is 1. It is repeated once. Am I right? This is what's called an algebraic multiplicity. Keep it in the back of your mind for later. And this number 2 is 10. So the algebraic multiplicity is 1. If I was trying to solve another equation, Mr. Ziyad, and I had in a 3 by 3 equation or something, this is eta minus 5 to the power of 2. Or eta minus 5 to the power of 3 for another equation, which means this guy is going to be a repeated root twice or 3 times. In this case, if it was repeated 2 times, I would say that this number has an algebraic multiplicity of 2, the number of repetitions of the roots. If I've tried to solve it once more for another a minus eta to the power of k, so I will call this guy with an algebraic multiplicity of k times. Simple. So once more, what's the algebraic multiplicity? The repetition of the root. The repetition of the root. The algebraic multiplicity is related to the eigenvalues for the geometric multiplicity. I've defined what's an algebraic multiplicity. Now I'm going to define the geometric multiplicity. What's the geometric multiplicity? It is the dimension of the eigenspace. What's the dimension also for any space? It is the number of vectors in its basis. If you look to this guy, how many vectors in its space? 1. So the geometric multiplicity is given 1. And also for this guy, the geometric multiplicity is also 1 vector. If I had 2 vectors here, then the geometric multiplicity will be 2. Okay, once more. What's the algebraic multiplicity? It's the repetition of the eigenvalue. What's the geometric multiplicity? It's the dimension of the eigenspace. From that, if the geometric multiplicity equal to the algebraic multiplicity, then this matrix is diagonalizable. If they don't equal to each other, then this matrix is not diagonalizable. Alright? Very simple. Okay? Now I will go through these steps once more for you. Please, do it once more for me. So the first step, I will get the eigenvalues, which is called spectrum. How to get it? Very simple. I will take the principal elements diagonal minus eta, all the determinant equal to 0. It will be called an equation. I will solve the equation, expand it. I ended up having eta 1 is equal to 5 and eta 2 is equal to 10. By the idea, never. It will make nothing or no difference if you choose eta 1 to be 10 and the eta 2 will be 5. So all what's going to happen is those guys will be replaced. Okay? So it's really not a big deal. The first step once more, these are the eigenvectors. Values. I will go now in order to solve the homogeneous system of equations, exactly as I told you, a minus eta I times u equal to 0. E here is stand for eta. Now, solving this, I will get this system. That's the system that I'm telling you, or that we use already. That's the augmented matrix. Are we okay? Now, go for the first vector. I will call it u1. You will call it v, w, whatever. So, actually naming it will make no difference. I'm getting the first vector relative to the first eigenvalue. Are you with me? Ziyad. Okay, the second step, I will use the homogeneous system, which is simply subtracting the eta 1 from the principal diagonal. Once you go, this is the system that we are dealing with. Once more simplified, you will find the 2 rows, there is a relation connecting them together. Get the reduced echelon form. That's the reduced echelon form. Am I right? So that's the first vector, first component. First vector, second component. That's a type we here. This is 2. The second step, you will have u11 plus 0.5, u12 equal to 0. So the relation here between the components, as yet,
Yeah.
u1 sub 1 equal to negative half u12. Alright? So the first vector contains how many components? Two of them. A, B. You can call them u1, this is the A, this is the B. It's up to you. x1, x2, xy, whatever. Okay. But as I told you, I prefer those ones for me, for myself. Okay? The second step, I will make the substitution. Eliminating this guy, I'm putting minus half u12. Now this vector depends on the value of u12. I will consider it 2, 3, 4, 5. It's up to you. It's an infinite number of solutions. I will prefer to choose 2. Why? Because I will have integrals. Am I right? So once you substitute with u12 with those elements, now you have the basis, once more, the basis for the eigenspace of u1. Okay? Which is negative 1 and 2. In a similar manner, I will do the same for u2. So once more, I will substitute instead of the eigenvalue 5, I will use the eigenvalue 10. Now I will have the same system. Okay, Mr. Ziyad? Solving the system is going to be really, very simple. Now you have the connection. It's in front of you. But in this case, the first component of the second vector is equal twice the second component of the second vector. Am I right? Once more, I will use the substitution. Eliminating this guy, I'm using 2u2. Here we go. Now be smart. Use the value that you will prefer in order to have integrals. I believe 1 is box tempting, because if you use 1, Mr. Ziyad, you will have 2 and 1. That's the second vector. Okay? Please look at these 2 vectors. Look to these 2 vectors. This is u1 and that's u2. Remark that if you multiply these 2 vectors in a dot product, u1 dot u2, or get the inner product of these 2 vectors, the result will be for this case, because you are working with a symmetric matrix. So those vectors are orthogonal. I will go to the next step. Any questions? Any questions whatsoever? Those steps for you, it's like just like that. This is the simplest part. The second part. Now I will go to step number 2. Getting the P matrix or the orthogonal matrix responsible about the diagonalization, which is going to be a very simple matrix. All I have to do is to get the first vector, the second vector,